Hello, my name is Autumn McSwain, and this is my Lab 2 Magnetic Fields of a Bar Magnet for Physics 2 over the summer. So, to begin with, the purpose of this lab was to measure the magnetic field of a small bar magnet. This is to help us better understand magnetic fields through a visual representation and to be able to play with dipole moments. And as you'll see later, the results are that N equals negative 2.9984, and the magnetic dipole moment is 4.613 AN. So, some fundamental principles before really getting to the lab is the Biot-Lovert law, which states that the magnetic field is generated by a steady electric current. This means that it has a electrical current that we know will act a certain way. So we have this formula, which is shown. And then another fundamental principle we need is the magnetic field of a dipole. This is important because magnetic fields of a dipole are closed circulations of electricity that are emitted off of magnets. So we are able to determine how the field will move using this formula because of how magnetic fields work with electrical currents. And then the final fundamental principle we will need is distance-dependent formula, which is used to find the magnitude of the magnetic field due to a bar magnet falls off with distance, which we'll be using the absolute value of B bar equal KRN. And then the linearized one where it's ln bx equals ln k plus n ln r will be used to find the dipole moment later for the coding. So this experiment procedure really had two big parts, or three big parts. So first, we have to orient the phone so that it makes a magnometer orthogonal to Earth's magnetic field. This means that it will create its own, which is why we put the bar magnet on the left on the ruler. And then we will find the magnometer chip of the phone, which is why there is the tape right there. And then we will measure the distance between the magnometer and the bar magnet for the on and off axis. So we will then put a tape on the actual bar so that we know the exact corner where we are going to be measuring our chip from. So in this, the magnet itself will act as the system and everything else will act as the surroundings. Okay, so for my on-axis data, this is what I got. The left is the data that I got at different electrical fields that were coming off. And then the right is my linearization of the data on the left. And through that data, I was able to get the function y equals negative 2.9984x minus 13.9896. This is important because this is linearized right now. So it is the same formula from earlier where it's the ln distance dependence formula, but it's shown like it's a linear. So I'm able to do some calculations to find both my n, which is negative 2.9984, and my k, which is 9.23 times 10 to the negative 7th, by using what I was given from the linear formula and converting it using the BR equals KRN formula. And then from that, we were able to find mu, where mu will equal 4.613 A times M squared. And then for the off-axis data, I was able to determine the off-axis field when it was 0.196 off. And to do an off-axis, this image is shown where I took another meter stick and put them perpendicular to each other, and then basically just raised it on the y-axis. So with all of this, I'm now able to do my computational model. And the computational model, this one was really important because I was just trying to define the magnitude of the magnetic moment or the dipole. And that was given to be found as 4.613, which is what I put in there. And then to actually make my computation model, there are three important parts. I have two that are on axis, two that are above the axis, two that are below the axis, and then I have one that is at a 45-degree angle going off the axis. And as you can see, my dperp changed to 0.196 for the vertical like it did in the experimentals, and that is how I was able to come up with the distance that is shown on the right. So, some assumptions and errors. So for the assumptions, the bar magnet must act as a magnetic dipole, and the magnetic field falls off as the distance increases. This is stuff that we have to assume is correct when going into this experiment. So due to this, there are a bunch of errors. The two biggest ones being that other electronic dynamics may skew with the data, like another device or my computer that I was reading from could have messed with the magnetic bar while I was sitting there trying to do it. And then also the exact location of the magnometer was not precise. And this is because I used one that was on my phone, and so it just wasn't like a completely correct one. So some of the observational statements are shown, but only the first and fourth one are true for this thing. So in this experiment, when the magnometer is far away from the magnet, it measures a near zero magnetic field in the x direction, as well as the magnometer moves closer to the magnet, the measured x component of the magnetic field increases. So for my what ifs, in the experiment, it was oriented to compensate for magnetic north, but if I hadn't done this and it was just laid at an angle with respect to Earth's magnetic field, how would this change the result? And Earth's magnetic field would interfere with the bar magnet's magnetic field, which would mess up the results. And then secondly, if I had two identical magnets that were put like stuck end to end, it would change my experiments because it would double the magnetic magnitude field, but the direction would still remain the same, as it would still be going the same direction, but the field would be longer. And that is my lab too. Thank you.